Good morning. So this is our 750 economic growth. And today we're going to study optimal economic growth. Let me share my screen now. Okay. So optimal economic growth. Now, there's one problem with the Solow model, and it's the dynamic inefficiency. Now, what is that? The question is this: since the saving rate is fixed, okay, in the Solow model, the question becomes whether the economy may or may not accumulate too much capital. Okay, so when I say too much capital, too much relative to what, right? So that's the question. Well, the Solow model does not really take into account the optimality of the accumulation path, right? If you compare this with a model where there's a planner and the planner chooses optimal consumption sequences, there's a certain difference in the understanding of optimality. Now, dynamic inefficiency again, basically over accumulation of capital, right? And let me show you this. So suppose that this is your Solow model, okay? This is your Solow model, and this is, as you know, investment per effective worker, right? Now write this in this way, okay? So let's think about consumption in a pretty simple way. So if I do not choose, if I do not take S as a given, but instead look at the paths where I can choose consumption, how can I do that? Well, the simplest thing you can do without explicitly defining a utility function is this. All right, in a steady state, this economy goes to a point where k dot is equal to 0, right? So in a steady state, whatever my consumption is, I have something like this. So C will be equal to f of k minus ng delta k, right? So in a steady state, this must be true even if I choose, even if S is different, right? Now you can ask, all right, then let's find the capital stock, that the steady state capital stock that maximizes steady state consumption. Okay. Now, obviously, you have what? You have f prime k star, right, equals ng delta. Okay. Then we have two different steady states. Okay. So one is the Solow steady state. Remember, in the Solow steady state, what do we have? We have S divided by ng delta 1/1 minus alpha. And then there is also this golden rule path, golden rule steady state. This is called golden rule, all right? So this is the one that maximizes consumption, okay? And this is equal to, so if I have f of k equals k alpha, I have alpha k to the alpha minus 1 equals ng delta, right? So K golden rule will be alpha, okay, so this is G, ng delta 1 over 1 minus alpha, right? Alpha ng delta 1 over 1 minus alpha. Now, as you see, the only terms that differ between these two states are there, all right? So what do we know? Well, we know that if steady state capital stock is equal to the K golden rule, we at least know that consumption at the steady state is maximized, right? So if we really care about consumption of people in the very long run, then K golden rule would be satisfying that optimality constraint, all right? But K solo is generally different, right? Because there is no guarantee that the society's saving rate is exactly equal to alpha, right? So there's no guarantee that. For this reason, if S is greater than alpha, what do we know? Well, what we know is this: society accumulates too much capital. Okay? In such a situation, okay, imagine that that's the case. All right? So S is given, alpha is given, and suppose that S is greater than alpha. So this is the case of dynamic inefficiency. And suppose this instead. Suppose that we decrease S. Okay, what happens? Well, if you decrease S, your initial generation, right at the point where the S, where S is decreasing, starts consuming more, right? And then in time, they keep consuming more. All right? So if you think about this, without decreasing the consumption of any generation, you can still go to a steady state. All right? So you increase steady state consumption, okay? So you increase consumption by decreasing the steady state level of capital stock. Okay. Now that's the thing that we don't like about the one of the things that we don't like about the Solow model, because it doesn't allow us to change, allow us to choose capital accumulation in a strictly optimal manner. All right. So that's the idea of optimal growth. So we have then a planning horizon, okay, a utility function of consumption, then a typical discounting term, okay, this is something you are familiar with. Now we want to maximize this, where we once again choose the consumption and then choose the capital stock, obviously. Okay. So that's the notion. So here, of course, rho is greater than 0, and G greater than 0, delta is between 0 and 1, right? And you know how to solve this problem, right? So you have the Hamiltonian, then you have the first order necessary conditions, right? And then you have the K dot C dot system, right? So you know how to characterize this. Okay. So if you do that, there's of course a transversality condition as well. So that type of model behave like this, right? So there is there's that. So this is K dot equals 0, and then there's this. This is C dot equals 0, and then there is a saddle path here, Okay, so the dynamics are like this. Okay, so dynamics are like this, and the economy converges to steady state, which is K star C star. Now, within such a framework, golden rule is where? Golden rule is here. Okay, right? So that's K dot equals 0, and golden rule is exactly right here. And you see that K star must be really optimal in that sense. Why? Because it is even lower than the K golden rule. All right. So there is no way that we can talk about dynamic inefficiency here. Why? Because we are choosing this path. You know, at the initial date, we basically jump on the saddle path and we converge to this point, and that entire path is optimal. All right. So we don't really care about what's the optimal level of consumption. We already know that it is optimal, right? Because we are solving it. Now, the second thing about the Solow model, the second thing we don't really like is this G. Okay, this is exogenous and fixed. Okay, in the Solow model. So we don't like that. We want to somehow understand how an economy grows in the long run, right? By the way, let me just remind you that. So we denoted, I guess, the output per effective labor in this way. So GDP per capita or GDP per worker was Y divided by L. So then in the long run, of course, the growth rate of Y tilde in some steady state is G, right? The growth rate of Y is G plus N. Okay. So we don't want, so we want to understand this. How can an economy choose a particular growth path? What determines G, right? So that is not answered in the Solow model. Now, the simplest optimal growth model, that will give you endogenous growth is the AK model. Okay, is the AK model, and this is how it works. So suppose that your production function is this. Okay, so this is, of course, I mean, if this is your Y, then this is Y, right? Because if you define Y here as Y over L and K here as K over L, okay? And labor can grow. It doesn't really it doesn't make a big difference. But the important thing is that once again, you are solving this endogenous, you are solving this optimal growth problem. So you have a utility function here, right? You have the utility function. Then you have your cost state variable. Then what you want to write here is, of course, K dot, right? And K dot will be like something like this, right? So it will be f of K. So f of K is AK, right? Minus CT. And here, I mean, you can have, of course, N delta, right? if you imagine that K dot is equal to K dot is equal to I minus delta K, once again, right? And if you imagine that investment will be equal to that, right? So investment per worker will be equal to YTLT minus CTLT. All right. Now this is your little c, and this is your AK. All right, AKT. So you can write in this way. All right. So of course you will have first order necessary conditions and other stuff. Okay. So what do you know here? Well, you have U prime C equals Q, right? Just a sec. All right. So U prime C is equal to Q. Then you have the constraint itself. So you have K dot T equals AKT minus CT. So this is, by the way, K here. So there's a K here, right? So N plus delta KT. So that's there. Then you will have the co-state equation. The co-state equation is this, right? Negative partial derivative of Hamiltonian with respect to capital stock. So what is that? Well, you have Q A minus M plus delta, right? Then you will have the transversality condition. Transversal condition will be limit QT times e to the minus rho t times kt equals 0. Okay, so this is pretty standard. All right. So if we proceed, to proceed, we have to assume a particular functional form for utility. Let's suppose at the simplest case, we have the logarithmic utility, right? So you have 1 over Ct equals Qt. Then you have K dot T equals AKT minus CT minus M plus delta KT. And you also have Q dot T minus rho QT equals minus QT A minus M plus delta. Okay, so that's correct, right? So let me make sure I'm all writing this correctly. Yes, there is one Q here. Okay. So what do I know? Well, if you do the math here, as we always do, so I have this. So then I have minus A minus N plus delta minus rho, right? So then from this, you have C dot T CT equals minus Q dot T QT. So you have C dot T CT equals A minus m plus delta so the sign will be rho. Okay. It's all correct, right? So what do I learn here now? Well, I think I have a sign problem here. No? All right, I mean, you can check later on. So the idea is that this model now tells you, okay, consumption in the steady state will grow. And of course, if consumption needs to grow, since consumption will be, I mean, there will be an upper limit for consumption, right? So your output level will determine how fast you can increase your consumption. But the idea is that if A is large enough, okay, if A is large enough, then C dot T divided by CT is positive. Okay. Now, what happens here? Well, we can understand growth as a function of parameters. Okay. Now, consumption grows in the long run because that's a steady state result. It's a balanced growth result. I will show you the details. But basically, we can explain growth. We find the economy's growth rate as a function of the parameters. Okay. So obviously, this is a balanced growth result. So if you want to write K dot T divided by KT, what do you have? Well, here you have AKT minus CT minus M plus delta KT. So you have A minus M plus delta minus CT over KT, right? Now, realize one thing. Along the optimal path, this will be constant, right? And since it is the, since this is constant along the optimal path, it is true for the steady state as well, right? So if you solve consumption, you will have something like this, right? So this is now the consumption growth rate. Now, obviously, in the long run, we want to also find this growth rate of capital stock being constant as well, right? But that requires the growth rate of CT and KT are the same, okay? So the growth rates must be same, right? Because there is this ratio here. So how do you do that? Well, you can define a new variable, xt, as this ratio. Then you tell me that there is a particular x star, okay? There is a particular x star that would equate K dot T KT to G, okay? Then you find this x star, all right? So we have now about 1 minute. Let me just pause here. So we are interested in a dynamic path, which will be optimal, right? Because we are solving this Hamiltonian problem. But in that optimal path, consumption and capital will grow, and consumption and capital needs to grow at the same speed, at the same rate. So let's meet at 9:55, okay? After I convert this video, all right? 9:55.
Okay.
All right, bye-bye.